All right, our next speaker is Gajendra Deshpande, and he'll be introducing us to how static analysis of Julia programs work. And actually, we have two talks on static analysis, one after this one. So if you'd like to learn more about it, then stay around. Then you can take it away. There we go.
Good afternoon, everyone. My name is Gajendra Deshpande from India, and today I'll be presenting a talk on static analysis of Julia code. Of course, I will not be going into the depth because there will be many techniques and many packages. So this will be an overview of static analysis packages in Julia and concepts. In today's talk, I'll be discussing why we should perform static code analysis, then types of static code analysis and packages, some code examples, limitations, and best practices. Now, this was the mission Mariner 1, so which failed in 1962. So the Mariner 1 spacecraft launched by NASA on July 22, 1962 was intended to fly by Venus and transmit data back to Earth. So however, shortly after launch, the spacecraft deviated from its intended trajectory. Then after investigation, they found out the cause. So the cause was the failure was traced back to a single omitted character in the guidance software's handwritten code. So specifically, it says that missing hyphen. Actually, it's not a hyphen. It was the bar on the radius r. Actually, so in the guidance equation led to the incorrect data being fed into the navigation system. So this error caused the guidance system to misinterpret normal minor variations in speed as serious deviations leading to rocket to veer off the course. Then the code error was a missing hyphen in the equation. Then the effect was the guidance system generated erroneous correction signals, which ultimately led to the spacecraft veering off course. So outcome was the rocket had to be destroyed 293 seconds after launch to prevent it from becoming hazard. The next was Ariane 501 explosion in 1996. So it was European Space Agency's Ariane 5 rocket exploded 40 seconds after the launch. Then the cause was the failure was due to the software error caused by an overflow. So a 64-bit floating point number related to horizontal velocity of the rocket was incorrectly converted to a 16-bit signed integer, leading to an overflow and software exception. So the code error was the unhandled integer overflow in the conversion. So effect was the exception caused the inertial reference system to fail, leading to the rocket losing control. So outcome was the rocket self-destructed, causing a loss of approximately $370 million. Then similarly, there were some other incidents. For example, Mars climate orbiter was lost its approach to Mars due to the navigation error, and the error was caused by the mismatch in the units between two software systems. So one system used the imperial units, that's the pound seconds, while the other used the metric units, that's the Newton seconds. So there were inconsistencies in the units in the software calculations. So outcome was the mission was a complete loss with a cost estimated at $125 million. Then there was another system that's called as Therac 25 radiation therapy machine. So it administered lethal doses of radiation to patients due to software errors, resulting in several deaths and injuries. So cause was the race condition and inadequate software safety checks. So the outcome was multiple deaths and severe injuries along with significant legal and financial repercussions. Then the next one was the Patriot missile failure in 1991. So the software error in the Patriot missile defense system led to the failure to intercept an incoming Scud missile, resulting in the loss of 28 soldiers' lives during the Gulf War. So the error was due to cumulative timing error caused by floating point arithmetic inaccuracy. Then similarly, there was another incident, that was the northeast blackout. So there was a cascading failure in the electrical grid, led to massive blackout affecting the parts of northeastern United States and Canada. So there was a software bug in an alarm system which failed to alert operators to a need to redistribute power after a transmission line overloaded and shut down. So there was a major blackout affecting millions of people and causing significant economic damage. So now these are the some incidences which highlight the importance of static analysis. Now let's see what is static analysis. It's a method of examining and evaluating the code of a software program without executing the program itself. Okay, so for example, we need not have to check the output. So without checking the output, we have to determine what are the problems. So there is a process in IT companies which many companies follow, that's called as code reviews. So it's also known as white box testing. So here you analyze the source code to identify the potential errors, bugs, even security vulnerabilities, then code quality issues, and other structural problems. So this process also helps us to ensure that the code adheres to certain standards and best practices. So there are certain standards related to every industry. So the code has to comply to that standards. Now key aspects of static code analysis. One is it is non-execution based, so we need not have to execute the code in order to check the output and check the functionality. Then automation. So developers write a lot of code, so it may not be possible to check each and every code manually and thoroughly. So in that case, automation and tools will help us. Then next one is early detection. So earlier you detect the problems, it is better for the software and the system, so that we can avoid the potential problems later. Then there are some comprehensive checks which are discussed here. So in comprehensive checks, we are going to perform the syntax checking. So here we ensure that the code follows the correct syntax rules of the programming language. The next is the type checking. So verifying that variables and expressions are used consistently with their declared types. Then we have something called as code metrics, measuring aspects of the code such as complexity and identify the areas that might be difficult to maintain. Then we also perform security analysis, detecting potential security vulnerabilities such as SQL injection and cross-site scripting flaws. Then coding standards, so ensuring that the code adheres to the established coding standards and best practices. Then benefits. So benefits are improved code quality, then enhanced security, cost savings, then there will be consistent code base, then your code is compliant to some standards. Then types of static code analysis. So when we consider types of static code analysis, there is syntax analysis, semantic analysis, type checking, data flow analysis, control flow analysis, abstract interpretation, code metrics analysis, security analysis, style analysis, resource and memory analysis, and concurrency analysis. So we'll go through all of these in brief. So first one is the syntax analysis. So it ensures that the code adheres to the grammatical rules of the programming language. So tools can be compilers and linters. So example can be the detecting missing semicolons or mismatched brackets. So here you can use a library called as Lint.jl. So it provides basic linting capabilities to detect syntax errors and common issues in Julia code. So by default, nowadays many programming languages including Julia have better error detection. So many times you may not need these basic libraries also. Then semantic analysis. So it checks for the meaning and consistency within code. So here you need advanced linters and static analysis tools with semantic capabilities. So example can be ensuring that variables are declared before use and that function arguments match their definitions. So here you can consider using the library called a static Lint.jl, so which is for static analysis of Julia code, which can be integrated with language server.jl. So that provides a semantic analysis, including checking for undefined variables, unused variables, and type mismatches. Then the third one is type checking. So it verifies that types of variables and expressions are used consistently. So here you have to make use of type checkers, compilers with type checking features. So example is ensuring that an integer variable is not assigned to a string value. So earlier there was a library called as type checking.jl, but it is not updated. But now we see that there is an alternative library which performs type checking, that's called as jet.jl. Then next one is data flow analysis. So here you examine the flow of data through the code to identify the potential issues. So you need here data flow analyzers. And the example can be detecting the use of uninitialized variables or the dead code. So you have this library here, sidalwho.jl, though primarily it's for exploring the type inference and optimization decisions. It can help understand data flow and identify related issues. And you can also use jet.jl here, so which performs comprehensive type inference and detects potential runtime errors, which often involve data flow issues. The next one is the control flow analysis. So here you analyze the order in which the instructions are executed. So you need here control flow analyzers. Then the example can be identifying unreachable code or infinite loops. So package which we can use is jet.jl, so which analyzes the control flow to detect issues such as unreachable code and potential infinite loops. The next one is the abstract interpretation. It basically uses mathematical abstractions to analyze the behavior of the code. So that's also part of formal methods. So tools that you can use are abstract interpretation frameworks. So examples include detecting potential runtime errors like division by zero error or buffer overflow errors. So you can use the library called as sai.jl, so that is static analysis infrastructure. So that provides a framework for building static analysis tools in Julia, so leveraging abstract interpretation techniques. Then you also need code metrics analysis. So that measures various attributes of the code to assess its quality. So tools can be code metric tools such as Sonar Cube, which is a third-party software. Example can be calculating the cyclomatic complexity to assess code complexity. So here code matrix analysis can be integrated into the existing packages to measure the various code metrics such as cyclomatic complexity. The next one is the security analysis. So it identifies the potential security vulnerabilities in the code. So here tools can be security analysis tools such as Checkmarks or Fortify. Again, these are third-party tools. So examples can be detecting SQL injection vulnerabilities or cross-site scripting flaws. These are specific to web applications. So we can think of security analysis here with respect to Genie framework, which is a Julia's web framework. So here security related static analysis can be integrated into tools called as static Lint.jl, or custom scripts can be written. And if you are considering web applications, here you can try to integrate OWASP top 10 rules. The next one is the style analysis. So that ensures that code adheres to coding style and conventions. So every language has got its own coding style and convention, so it has to adhere to that. So tools can be again linters and type checkers. So example is enforcing consistent indentation and naming conventions. So the packages which we can consider are document format.jl, which automatically formats the Julia code according to the style conventions, so helping to enforce consistent style. Then there's another library called Julia formatter.jl, which is a highly configurable formatter for Julia code, which helps enforce code style guidelines. The next is resource and memory analysis. So it identifies the potential issues related to resource and memory usage. So again, tools can be static analyzers with memory analysis capabilities. So example is detecting memory leaks or improper handling of file descriptors. So you can consider a library called as valgrind.jl, which is a Julia wrapper for Valgrind tool. So which is typically used for dynamic analysis, but can be integrated with the static analysis tools to provide comprehensive resource and memory analysis. The next one is the concurrency analysis. So it analyzes multi-threaded code for potential issues related to concurrency. So here we need to make use of concurrency analyzers. So examples are detecting race conditions or deadlocks. So here you can use a library called as threadsanitizer.jl, which is a tool for dynamic analysis to detect race conditions integrated with Julia's threading model. So static analysis for concurrency might be integrated into existing tools like jet.jl for early detection and potential issues. Now let's consider an example here. So we have a static code analysis example. There's a simple function written here which just adds two numbers, and there is another function called as example, and there is some variable which is named unused variable, and we are not using it anywhere in the function. So our static analyzers should be able to detect such variables. So then in the next step, so in the previous step what we have done is we have created the code and saved it as example.jl. Then next in this step we are using static lint library, then we are using symbol server and language servers, and we are setting a file path. Then we are using the static lint.document.method. Then we are running the checks on the code, and we are printing the issues using a loop. Then when you see the output, you are going to get the output like this. For example, it says unused variable. So unused variable is assigned but never used. So this is the message we are getting. So we have to resolve these issues. And you can also see that in the function example, unused variable equal to 42. This line is highlighted. The next example is using jet.jl. So here we have some multiple functions. So one is faulty function, then second one is the unused variable example function, and third one is the divide by zero exception function. And in the main function we are invoking all these functions. So in order to use the jet library, you have to first install it, and after installation you can say using jet. Then you can include this line @report underscore include faulty code.jl. The entire code, whatever you want to check, that has to be saved in a Julia file, and then that Julia file name can be passed as a parameter here for analyzing. And this is the output you get here. So you can see here that there are multiple issues which are identified here. So one of them is again unused variable, then second one is possible divided by zero error. So there was another issue here in the faulty function, that was the type instability. So we have to modify the code and we have to fix it. This is the fixed code where we have fixed the type instability. Then here in this function unused variable was there, so we removed the unused variable. Then in the previous case, we had written a code which was potentially leading us to division by zero error. But now we have handled it, so we can avoid the division by zero error. So then next is limitations of static code analysis. So there can be false positives and false negatives. So it's a common problem. Some problems may go undetected with static analysis. Then there will be limited context understanding. So your code analyzers may not understand the entire code and their semantics. There will be performance impact. Then complexity and scalability issues will be there. Then lack of semantic understanding. Then you need to configure and customize the static analyzers to suit your needs. Then limited security analysis, because security is again a different game. So there are many issues with respect to web applications, system applications, and so on. Then there are integration challenges, because you need to work with multiple code analyzers. It may not be just multiple static code analyzers. It may be static code analyzers and the dynamic code analyzers as well. Then there will be dependency on the language and the environment. Then next one is the best practices of static code analysis. So it's often said that you integrate early and often, so that you can detect the problems early. So here continuous integration CI/CD pipeline is strongly recommended. Then next is automate the process to run the static analysis tools, code commits and pull requests, etc. Then use multiple tools, because a single tool may not be sufficient to detect all the problems. Tools will be having limitations. So it is better to use multiple tools, and depending on our objective, we can select the tool. Then customize and configure the tools, because these tools are basically, they work on specific issues. So you may have to customize these tools to suit your requirements. Then review and act on findings. So you need to perform frequent code reviews, frequently the output of these code analyzers, and act on the findings. Then educate and train the developers. You need to create the awareness among the developers regarding how to use these static analyzer tools, so that they can start reading the problems and start resolving them. Then incremental analysis. So you do not have to perform analysis only at the end. So you can perform analysis as soon as you write the code block or a module, so that you can detect the problems early and find the solutions. Then you can also measure and monitor the output of these source codes. Then integrate with code reviews. It may be process, it may be tools. Then use the community and use the community forums and other platforms to get the updates, or even to get the solutions, or even to get the best practices, suggestions, and so on. Thank you for everyone. Thank you for giving me an opportunity to speak here. Thank you.
All right. Is there any question on the audience? Oh, over there. Okay.
On one of slides you showed the Valgrind.jl. Where can I find it?
You can find it in GitHub repository.
I tried to search. I cannot find it on a Julia Hub or on a GitHub.
Okay, fine. You can contact me after the talk. I'll share the link.
Okay, thank you.
Thank you.
We had another question over there.
Thank you for your talk.
Thank you.
You presented various packages, I understand. Do you have any statistics about usage of these packages? Are they used often and which kind of companies? How does it work in practice?
I don't have any statistics, but if we go to the repositories of open source projects, then we may find some statistics.
You mentioned a bunch of real-world examples of software bugs causing problems. Do you have any sort of analysis of what proportion of software bugs could be caught by software static analysis, especially in the context of Julia?
No, I don't have any idea.
Okay.
Thank you.
All right, any other question? If not, let's thank Gajendra again.